Welcome to the new era of video creation with Biozy 8. Today, we will discuss designing an AI system that can handle multiple tasks simultaneously. How would you approach designing an AI system that can handle multiple tasks simultaneously? Multitask learning. What are the challenges and how would you address them? Multitask learning, MTL, is a subfield of machine learning where a model is trained to perform several tasks at the same time, instead of training separate models for each task. This approach takes advantage of shared knowledge between tasks, allowing the model to generalize better and learn more efficiently. By learning from multiple tasks, the model can leverage shared representations of data, improving performance across all tasks. In practice, MTL has been widely used in domains such as natural language processing, NLP, where a single model can be trained to handle tasks like text classification, sentiment analysis, and named entity recognition simultaneously. It is also used in computer vision, where a model might be trained for both object detection and segmentation tasks. Similarly, in robotics, multitask models can be trained to handle multiple operations like navigation and manipulation. The main challenge in MTL is managing the balance between tasks. It's important that the shared representations are useful for all tasks and not detrimental to any specific task. While multitask learning offers several advantages, it also comes with specific challenges. Task interference is a key challenge in MTL. In some cases, the model might learn features that are beneficial for one task but are detrimental to another. This can happen when the tasks are not closely related or when they require conflicting features or representations. Imbalanced task importance occurs when one task is much more complex or requires more data than others. The model might focus more on the dominant task, leading to suboptimal performance on the other tasks. Optimization difficulty arises because each task may have a different optimization goal, such as different loss functions or performance metrics. This can complicate the training process and require adjustments to the learning rate, gradient updates, and loss weights for each task. Task-specific requirements involve challenges like different output formats or model architectures for each task. For example, one task might require classification, while another requires regression, making it challenging to design a single model to handle both efficiently. To address these challenges, different model architectures can be used in multitask learning. Shared backbone. In this architecture, all tasks share a common feature extraction network, which is followed by task-specific heads, output layers. Each head corresponds to a different task. The shared backbone allows the model to learn general features that are useful across all tasks, while the heads specialize in generating predictions for their respective tasks. Hard parameter sharing. This is a form of multitask learning, where some layers, typically lower layers, of the network are shared between tasks, while higher layers are dedicated to specific tasks. This ensures that the model learns general features in the shared layers and task-specific features in the specialized layers, helping prevent task interference. Soft parameter sharing. Here, each task has its own model, but certain parameters are shared between the models. This allows the models to specialize in their respective tasks, while still sharing useful information at higher levels of abstraction. Handling multiple tasks in a multitask learning setup requires careful design of the loss functions and how they are combined. Each task may have its own loss function, such as cross-entropy for classification or mean-squared error for regression. The key challenge here is combining these losses into a single scalar value that can guide the learning process. Loss weighting is one approach where each task's loss function is multiplied by a weight before being summed up. The weights help balance the importance of each task during training. For instance, if one task is more important or harder to learn, you might assign it a higher weight. Handling multiple gradients during backpropagation can be tricky since each task's loss contributes a gradient to the shared model parameters. It's crucial to ensure that gradients do not conflict with each other, potentially slowing down learning or causing instability. Adaptive loss weighting is another strategy where the loss weights are adjusted during training based on the performance of each task. For instance, if one task is lagging behind, its weight might be increased to accelerate learning. In multitask learning, the relationship between tasks is critical to the model's success. If the tasks are closely related, sharing knowledge between them can significantly improve performance. For example, in computer vision, tasks like object detection and segmentation often benefit from shared features because they both rely on understanding object boundaries and shapes. These types of related tasks can effectively use a shared model to enhance each other's performance. On the other hand, tasks that are very different, e.g., image classification and text generation, might not benefit from shared knowledge and could even interfere with each other. In such cases, the model might require more sophisticated strategies such as task-specific architectures. Transfer learning can be a great tool when tasks are related. A pre-trained model can be fine-tuned on a new task, leveraging knowledge learned from related domains. Finally, task prioritization helps ensure that critical tasks are optimized first, especially when some tasks are more important for the model's application than others. Optimizing multitask learning models requires several specialized techniques to handle potential conflicts between tasks and ensure stable learning. Gradient clipping is used to avoid exploding gradients, a common issue when multiple tasks contribute conflicting gradients during training. By limiting the gradient value during backpropagation, gradient clipping ensures that updates remain stable. Shared and task-specific optimization ensures that shared parameters and task-specific parameters are optimized separately, allowing each task to have its own learning rate or gradient update rule. Learning rate schedulers can be used to adjust the learning rate for different tasks. For example, if one task is converging faster, its learning rate can be reduced, while the learning rate for slower tasks can be increased. Curriculum learning involves introducing tasks in an easy-to-hard sequence, ensuring that the model first learns simple tasks before moving on to more difficult ones. This helps improve stability and reduces task interference. In practice, managing the scalability of a multitask learning system is crucial. As data grows, you may need to adapt the model architecture to handle the increasing number of tasks or the size of the dataset. Ensuring that the model can scale without degrading performance across all tasks is an ongoing challenge. Multitask learning has a wide range of applications. In NLP, models like BERT are trained on multiple tasks, enabling them to perform tasks like question answering and text classification simultaneously. In robotics, multitask models can handle tasks like navigation and object manipulation, while in healthcare, models can be trained to perform diagnostic tasks alongside patient outcome predictions. Choosing the right tasks to include in the model is a key decision. You need to ensure that tasks are sufficiently related to benefit from shared learning, but not so different that they cause interference. Finally, evaluating multitask performance requires careful consideration of metrics, as some tasks may be more critical than others. In summary, multitask learning is an efficient and powerful technique, especially when tasks are related and share common knowledge. The key to success in MTL is selecting tasks that benefit from shared representations and designing the model architecture accordingly. The shared backbone with task-specific heads is a common and effective approach. When optimizing, it's important to manage gradients, loss functions, and task priorities to ensure stable learning. Real-world applications like NLP, robotics, and healthcare showcase the potential of MTL, but also highlight the challenges of balancing tasks and optimizing the model effectively. By considering these best practices, you can build efficient multitask models that are scalable, stable, and perform well across a range of tasks. Multitask learning is an exciting area in machine learning, offering a way to build models that can handle a variety of tasks simultaneously. It has the potential to reduce redundancy in model training and improve efficiency by leveraging shared knowledge. However, it comes with its own set of challenges, particularly around task interference, optimization, and balancing multiple loss functions. Future research and development will continue to explore new ways to improve multitask learning models, addressing these challenges and discovering innovative methods for task-specific optimizations. As AI models become more sophisticated, MTL will likely play an increasingly important role in building systems that can tackle complex real-world problems. In conclusion, multitask learning is a promising approach that has the potential to revolutionize the way AI systems are designed, allowing models to handle multiple tasks simultaneously. By understanding the key challenges, selecting appropriate tasks, and implementing robust architectures, you can unlock the full potential of MTL and apply it to real-world scenarios, from healthcare to robotics. With ongoing research, the future of multitask learning is bright, offering exciting opportunities to improve AI systems and make them even more versatile and efficient.